Okay, Chapter 4, Section 2. In this section, we're going to learn about the least squares regression line. We're going to use this line to make predictions. We're going to interpret slope and the y-intercept of the least squares regression line, and then we're going to compute the sum squared residuals. Okay, so let's learn what all that is. Let's begin with an example. Let's say we have this table of values. There's no interpretation of these quantities at this point, so we're just going to work with the numbers. And we're going to start by creating a scattergram and then determine the R value for these table of values. Okay, so let's just assume that this is the explanatory variable x and this is the response variable y. And we just want to establish if there's a correlation between these. So we're going to create a scattergram. Let's begin by using our calculator since we learned how to do that in the previous section. Okay, so let's go to Stat, Edit, and I don't need any of these things. So I can go one by one and delete them, or I can hit Stat and then Clear List, and then I can do L1, comma, L2, comma, L3, comma, L4, comma, L5. I'm not sure if I needed also to clear L6, but might as well. L6, so that should clear all of them up. Done. Done, done. Okay, Stat, Edit, and boom, clean slate. Okay, so we're gonna first of all input all the x coordinates onto list 1 and all the y coordinates onto list 2. Okay, so this is gonna be list 1 going that way, and this is going to be list 2 going that way. So we have 0, 2. Okay, so there, we've inputted all our values, list 1, list 2. These are our x coordinates, these are our y coordinates. So they constitute ordered pairs, and then we're going to use our calculator to create a scattergram. We're going to go over to y equals, confirm that there are no equations there to bother us, or if there is an equation there, that the equal sign is not dark, right? That means that it's been deactivated. Also look up here, make sure that only one plot is active, in this case plot 1, because it's darker, and that the others are deactivated. We don't want more than one to be active, just the one we're working with, which is going to be plot 1, so it's okay that it's on. Okay. Next, we're going to go to stat plot, so second, stat plot. And from this window, we can see an overview of what's going on. So plot 1, plot 2, and plot 3. Plot 1 is on. It's currently set to a scattergram of list 1 and list 2. That's in fact what we want. Plot 2 is off, plot 3 is off. That's perfect. So hit enter. Okay, on. That's good. And like I said, right now it's already been pre-selected to be in the scattergram setting, so that's good. Next, it wants to know where the x coordinates or the input values are. List 1, that's good. And then the y coordinates on list 2, that's good. Okay, now we're going to hit zoom, and then the 9th option down. You can either hit 9 or you can scroll down and then select 9 and hit enter. And there we go. So here's what that scattergram looks like. And then if we wanted to know what each of these individual values are, we can hit the trace button. And we can see that that little blinking X in there means that this is the coordinate 0, 5.8. That's this first one. And then we go to the right by 1. And then that one is 2, 5.7. 2, 5.7. And then 3, 5.2. 3, 5.2. Okay, so here's our scattergram. Let me see. We can use this information to draw a sketch. Also, keep in mind that this is not necessarily the x-axis, and this is not necessarily the y-axis, but I think it is because this is 0 there, right? Okay, so let's go over to our window and check. See how it goes slightly into the negatives along the x-axis. This is negative 0.6, and this is 6.6. That means that this point right here is negative 0.6, while this point over here is 6.6 along the x-axis, which means it does include the y-axis. Good? Okay, but looking at the window for the y, it starts at 1.2 to 6.4. That means that this is 1.2. It does not go into the negatives, therefore it's not showing the 0. It's not showing the x-axis. If we want to see it, we got to go over here, go to y min, and pick something. Now, if we pick something that's too big, like -10, big in relation to how big the y maximum is, right? So if I choose that, and then I have to go to zoom and then number 9 again. Oops, sorry. Window, and then go down to -10, enter, and then hit graph. And you see that now -10 is way down here. There's all this empty negative space that we just, we don't need it to be there. Okay, so pick something that's gonna, give you a small little gap just so you can see the x-axis, but not create a huge gap that causes a problem. So how about -1? You can just kind of guess and check different things until it works. Oh, I messed up. That was the wrong answer. Go to zoom, number 9, get it back to the way the calculator chose the window, and then let's go down here to y minimum and then hit -1 there. And now graph, there we go. So that looks better. So this is a nice little picture of our scattergram. And remember that from here we want to kind of ballpark, right? If it looks like perhaps it has a relationship, a linear relationship. And just from eyeballing it, I would say so. There seems to be something that kind of goes down this way, right? Let me see if I can take a picture of this. Okay, so here's my scattergram. You can easily use your results from your calculator to draw this or sketch this by hand. And then from here, step 1 is to kind of eyeball it, and it looks like a pretty fair guess that there is a linear relationship somehow this way, something in that direction-ish, right? Meaning that as the input variable gets larger and larger and larger, right, as this goes this way, the output variable gets smaller and smaller and smaller, right? Like if I told you there's this new value is right here, what do you think the output is? Do your best guess. My best guess would be somewhere in this zone here, right? I wouldn't guess up here. That would be a bad guess, right? Or if I told you there's this new point, it's over here. This is the input, what's the output? I wouldn't guess that the output is right here. My best guess is that the output is way up here, right? Just kind of falling in line with the pattern of the rest. That's what it means for us to have a negative linear relationship when as the input variable gets larger and larger, the output gets smaller and smaller. And as the input variable gets, let's use a different color. And as the input variable gets smaller and smaller and smaller, the output variable seems to get larger and larger and larger. Good? Okay, so there seems to be a negative linear relationship, but that's just eyeballing it. That's just kind of looking at the data and kind of guessing it. But we could do better than that. We learned in the previous section that we can calculate the R value. Okay, so this is a great opportunity to practice that. So let's do that using our calculator to sort of do it by hand, but we're still going to use our calculator to do all the heavy lifting with all the arithmetic. Okay, so I'm just going to map it out. Now, when you're asked to do this on your homework or on a test, I would recommend that you do it in the following way. We need a nice table to organize all our information. So I need 1, 2, 3, 4, 5, 6, at least 7. 1, 2, 3, 4, 5, 6, something like that. Okay, so I'm going to have a column for my x coordinates. That's going to be the 0, 2, 3, 5, 6, and 6. And I'm going to need to know the x mean and the standard deviation for just the x coordinates. Next, I'm going to do a column for the y values. That's 5.8, 5.7, 5.2, 2.8, 1.9, 2.2. Okay, and then I'm also going to need to know the mean of the y's and the standard deviation of the y's. Okay, luckily we have our calculator. We don't have to do all that work by hand. So I've already inputted all my values for the x coordinates onto list 1. So I'm just going to do a one variable stat on list 1. Calculate one variable statistics on list 1, and anything and everything I want to know about list 1 will appear, including the mean and the sample standard deviation. So by default, I'm going to go out to 4 decimal places. Right? In this class, by default, always do 4 decimal places. So that's going to be equal to 3. This is going to be 3.6667. And the sample standard deviation is 4121, 2.4121. Good. Now we want to do the same thing for the y coordinates. So again, I already have all my y coordinates listed onto list 2. Stat, edit, hit enter. List 2 has all my y coordinates. So I just need to do a one variable statistics on list 2. One variable stat, list 2, enter, enter, calculate. Everything I need is right there. So the mean is 393. $33, 3.9333, and then the sample standard deviation. And I know it says X is on here, but that's because your calculator is not very bright, right? It just uses X's for everything. We have to know that even though it says X is on here, really we're talking about list 2, which contain the values of this list. So don't let that confuse you. Okay, so the sample standard deviation is 1.8239. 8239. 1.8239. Okay, so now that we have those values, remember our formula is going to be to find the z-score of each x, each y, multiply them together, and then finally add them all up. So I need a column here for the z-scores of x, z-scores of each x value, which is equal to each x sub I value minus the mean for the x's divided by the sample standard deviation for the x's, right? Well, in my calculator, that's list 1, and this is list 2. So what I'm going to want to do is create a new list here, list 3, which is equal to list 1 minus the mean, which was 3.6667, divided by the standard deviation for the x, which is 2.4121. 2.4121, getting it from down there. It's a little too big. Okay, so now let's go over to my calculator. Stat, edit, list 3 is going to be equal to parentheses L1 minus 3.6667 divided by 2.4121. Enter, and there we go. That's all the values I need. So I can copy those onto here. So this is negative 1.52. And now if I want a more detailed answer, right, so let's just round it off a little bit, but the more detailed answer is down here. But just for the purposes of this, I just want this to drive the process. Ultimately, I'm keeping all my accuracy in my calculator. So for now, I'm just going to put that in here, 0.691, negative 0.276, 0.5528, 0.9673, and also 0.9673. Okay, those are the same because these are the same. Okay, so I didn't put that much accuracy into here because ultimately I'm actually calculating it with my calculator and I'm keeping like 10 decimals of accuracy on my calculator. Well, that's based on me using already some rounding values of 4 decimal places, so that's how much precision we can rely on, or one less than that, 3. At any rate, so we're going to keep those in there, and now we need to make a new column for list 4. And list 4 is going to be the same thing, but for the y values. I need the z-scores associated with each y value, which is going to be equal to y sub I minus y bar divided by s sub y. So that's going to be list 4 equals list 2 minus the mean of the y's, which is 3.9333 divided by 1.8239. Okay, so going back to my calculator, I got to go to the right, go up, and then list, oops, let's put a parentheses there. What just happened? Calculate, edit, go up to list 4, and then we're going to do parentheses, list 2 minus 3.9333, close parentheses, divided by 1.8239. There we go. Okay, so these are all of these values. So this should be 1.0235, 0.9686, 0.6945, negative 0.621, negative 1.115, and negative 0.95. Good. Okay, so the next thing we need to do is another column that has the product of all of these. If you are feeling a little lost right now, you should go back to the other section where I did this in a little bit more detail. So here I'm just kind of going through it a little bit faster. So list 5 then is going to be the product of these two. That's the next phase in our formula to calculate the R value. List 3 and list 4. Okay, well here there's no nothing mysterious. We just have to multiply the values of list 3 and list 4. So let's go over our calculator and go to the right, go up, and we're going to do L3 times L4, enter, and then those are the values onto list 5. So let's put that over here. So this should be negative 1.556, negative 0.669, negative 0.192, negative 0.92343, negative 1.078, and negative 0.919. Okay, and then the next step in our formula is going to be to sum these up. So we want the summation of all of these, sum these up. So that's going to be, we can get that by doing a one variable stat on list 5. Stat, calculate, one variable statistic, list 5. Enter, enter, enter. And then right here, this is what we want. Remember, we don't care about the mean of list 5 or the standard deviation of list 5. We just care about the sum of all the values in list 5, and that's what this is. So the sum of all these numbers is negative 4.75, say 7582. 7582. Okay, so that takes care of the heavy lifting in the arithmetic needed to calculate this. So now we can go back to our formula. So remember the formula for R is equal to this giant fraction where we have x sub I minus x bar divided by s sub x times y sub I minus y bar over s sub y, and then we want to sum all those up and then divide by n minus 1. Okay? All right, well, we calculated all of these. These are all the values on my list 3. These are all the values on list 4. I multiply them. Those are the values on list 5. And we found the summation. So far we have that R is equal to negative 4.7582 divided by n minus 1. And n minus 1, in our case, how many values are there? So that's what these are. There's 1, 2, 3, 4, 5, 6. So for us, n equals to 6. So this would be equal to 6 minus 1, or 5. So R equals to negative 4.7582 divided by 5. And that is equal to, let's go back over here, clear, quit whatever you have there going on there, and it's negative 4, let's squeeze this over here. It's going to be negative. Make sure you use, clear. Make sure you're using this button for negatives, by the way. This is subtraction. If you hit that, you're going to get a different result or an error. Okay, so negative 4.7582 divided by 5 gets me to negative 0.9564. Negative 0.95164. Okay, so as we saw yesterday, or in the previous video, that indicates that we have sufficient statistical evidence to conclude that there is a strong negative linear correlation between the x-coordinate values and the y-coordinate values. All right, that's what we conclude here. We've mathematically proven that there is a strong linear relationship, negative linear relationship between the x-coordinates and the y-coordinates. Good. Okay, so we created our scattergram. Let me erase this. Oops. We created our scattergram. Here's our scattergram. And then visually, it looks like there is a negative linear relationship. So right away, we kind of suspected that. And then we did this really, really long, tedious calculation to figure out the R value, the correlation coefficient value, and it confirms our suspicion that there is a strong negative linear relationship. Okay, so now the question becomes, well, what is that relationship? What is a line that does a good job of approximating that negative linear relationship so that we can use it as a good way to approximate unknown values? Okay, so how do we guess what that would be? Okay, so in this section, that's what this section's about. Let's figure out a good approximation for that negative line. Um, the first way that we're going to do this is by simply using a couple of points and identifying those 2 points and then finding a line that connects them. So you got a little bit of freedom to choose whatever you like, but there are some good choices and there's some bad choices. So for example, if I chose the first point and the last point, just kind of focus your attention on those, and I drew a line that connected those two, it might look something like this, pretending that's straight. So maybe we might think that that red line does a pretty good job of expressing that negative linear relationship. Maybe. Someone could argue that that is a good job. Somebody else might decide, you know what, maybe a better guess would be this one and this one. Who knows? Maybe that's a good guess. So maybe they would grab these two and go right down there. Again, pretend that's a straight line. And so maybe that's a pretty good job. Maybe that green line does a good job of expressing that negative linear relationship, right? So this first method, this first thing that they're going to ask you to do in your homework is to pick a couple of points. Now they might give them to you and say, use this point and use that point, or it might be up to you. Keep in mind that there are several good choices, like the first one and the second one, or maybe this one, but there's also sometimes at least one terrible choice. Like if we choose these two, for example, we would end up with a line that looks like that. And then this red line would not do a good job of expressing the negative linear relationship that exists between those two, right? Also, this point and that point, I think would also do a terrible line of expressing the relationship that exists, right? Again, pretend they're straight. It's straight adjacent. But a line like this doesn't really show that negative linear relationship that we think exists, right? Okay, so there are some poor choices, although there are lots of good choices. It's up to you to kind of decide what would be a good choice. So let's use technology to further, give some other examples of where we could have a scattergram and how we might guess what a good choice is and what a good choice isn't. Okay, so let me go over here. Okay, so you can just Google Rossmann-Chance applets if you like and find your way to here. And I'm going to play with this one right now. Least squares regression. Click that. And for now, I'm just going to play with part of it. Let me zoom in here. Oh, too zoomed in. Okay, so we have some data here. Looks like the input values are foot length, and then the output values are the heights. Okay, so how long is your foot? And then over here is how tall are you? And it seems reasonable that there is a correlation between them, right? The bigger your foot is, the taller you are. The smaller your foot is, the shorter you are. Although it's not a perfect relationship. There could be somebody who's pretty tall and has kind of relatively small feet compared to how tall they are, right? So that would be maybe somebody, look at this person right here. This is how tall they are, and this is their shoe size. But then look right underneath there, there's another person that has the same shoe size, but it's a little shorter. Here's another person that has the same shoe size, but is a little shorter. Good. But there seems to be kind of a positive relationship this way, right? There seems to be something going that way. So we could kind of guesstimate it. That's what I want to do. I want to guesstimate where that line would be. Show movable line. Let's do this one. Okay, so with this right now, all I'm doing is kind of guessing what it would look like. So maybe this blue line does a pretty good job of sort of establishing the direction of our positive linear relationship. I mean, we sort of kind of want an average here. We kind of want half the little dots to be above the blue line, about half of them to be below the blue line, to kind of give you a good idea. So at this point, we don't really have a right or wrong answer here. We're just saying someone could guess it's this one. On the other hand, someone could guess it's that one. On the other hand, someone could guess that that one's the better answer, or someone could guess that maybe it's that one's the better answer, right? So there are lots of different lines that make a good guess. But initially, what we're going to do is, and so our guess doesn't have to go through any of the original data points. Like say this line right here, this guess, notice that none of the original black dots are on this blue line. And maybe that's the perfect way to describe that positive linear relationship. But initially, what we're going to do is to find a couple of points, like let's say maybe this point and that point. Maybe you're convinced that that's the way to do it. So maybe find a line that contains that point and that point. Maybe that's what you guess is a good approximation. And then we're going to find the linear equation of the line that contains those 2 points, right? Or maybe you think that it's these two. These two right here make a good approximation. So we would find the linear equation that contains those 2 points. Right, so maybe you're just focusing on these two. At that point and that point, you're thinking, okay, let me find the line that contains those 2 points, find that line, and that would be a good approximation for that positive linear relationship that exists amongst the whole thing. Good. Okay, so let's go back to this guy. Okay, so let's go back to our calculator. Let's go back to our graph. Here it is. How do we choose that? Let's just pick a couple of points. Maybe the first point and that point would be a good guess, right? So there's several good guesses. Let's use the trace feature. Maybe this point right there, and maybe this top one, or maybe this one. Yeah, that seems like a good guess. Maybe this point and that point. So I'm going to use the point 0, comma, y equals to 5.8, as well as 5, comma, 2.8. Okay, that's just a choice I'm making based on my graph. I'm thinking that if I draw that line, it'll do a pretty good job. Okay, so let's go back over here. Let's go back to our table. And I'm saying I want to find the linear equation that goes through this point and this point. Right? So for part B, find a linear equation that relates x, the explanatory variable, to y, the response variable, by selecting 2 points and finding the equation on the line that goes between them. And those are the 2 that I'm choosing based on my scattergram, right? So that would be this point right here. This is the 0, 5.8. And this one, which is the 5, 2.8. I'm going to find the equation of the line that goes through those 2 points, and then that will be a pretty good approximation to the data. Okay, so let's do that down here. So now the question is, given 0, 5.8 and 5, 2.8. Double check if those are the right values. 5, 2.8. Okay, so given these 2 points, find the equation line that goes between them. Okay, so there's a couple of different ways to find the equation line that goes between 2 points. So one popular way to do that is to go through this equation, find m, and then that's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Once you find m, the slope, right, this is the slope. Once you find the slope, then you can either use this equation, which is y minus y sub given, you need a given ordered pair, equals to m x minus x sub given, right, where m is the slope, and then x sub g, y sub g is some given value, right? So you need to have one ordered pair and the slope. That's one way to find your equation. And the other way, the other formula that's also popular is to use y equals mx plus b, right? Where this is the slope, m is the slope, and 0 comma b is equal to the y-intercept. Good. Okay, let's go through this process since I think that that's what the author likes to use. So step 1 is going to be to find the slope. So let's find the slope. It's going to be y equals 2. Okay, so let's label these guys. Let's just call this one 0.1, so that would be x1 and y1. And this would be x sub 2 and y sub 2. So we end up with 2.8 minus 5.8 divided by 5 minus 0, right? Y sub 2 minus y sub 1, x sub 2 minus x sub 1. Okay, so we end up with negative 3 divided by 5, which gives you negative 0.60. There's our slope. Okay. Next, we want to use this formula, and one of the points we have, well, actually we have 2 points on our line. We could use either one, but why not use the easiest one? And anytime you see a 0 in anything, it usually ends up working out nicely. Depends on what you're doing. But in this case, it works out well. So we have y minus, and then I'm going to use the 5.8, is equal to negative 0.60, the slope, times x minus the 0, right? That's using this point and the slope. Okay, so now all that's left is to distribute, simplify, solve for y, and we get our linear equation. So this is going to be y minus 5.8 equals, and then when I distribute, anything times 0 is 0, so that term disappears, and I end up with 6.0 times x. And now if I just add 5.8 to both sides, I end up with y equals negative 0.60x plus 5.8. There's my linear equation. Okay, it's got a slope of negative 0.60 and a y-intercept of 0, 5.8. Well, actually, obviously, that had to be the y-intercept just because it just so happens that one of the points that I chose was on the y-axis, so it had to be that. Okay, so now I can go back to my calculator and confirm that that's a good approximation. So I'm going to go back to y equals, remember it was the line that connects this point and that point, so I'm going to go to y equals, and I'm going to type in that formula. So I'm going to type in negative 0.60 x plus 5.8. Enter. Okay, so there's my line. Notice that this one is deactivated because the equal sign is not dark. But you know what? I don't really need it, so I'm just going to hit clear and erase it. So here's that line. The equal sign is dark. Make sure that you use this to represent negatives and not this, which is a subtraction sign. Okay, now that I have that, I can go ahead and hit graph, and it's going to do both. So we have my scattergram in the background, and now I have that line that's hopefully a pretty good approximation. If you have a color screen, I can also change the color so it pops out a little more. So let me go over here and see how we have blue right there. So let me come over here and hit enter. And then I can change the color. Let's change it to green. Enter. And then graph. What happened? Oh, I didn't hit enter. Hit enter. Hit green. Hit enter. Enter. Okay, there we go. Now we can hit graph. There it is. Okay, so there's that green line. This is this equation, right? And it goes through this point there and that point there. I can hit trace. So it goes through the point 0, 5, 8. And it also goes through the point 5, 2.8. And I think that does do a pretty good job of expressing that negative linear relationship that exists between these two variables. Good. But it was just a guess, and I did just kind of pick those 2 points. Someone else could easily pick a different set of values, and I believe that's what the author did. So let's see what the author did for this question. So the author picked the point 2, 5.7 and the point 6, 1.9. Okay, so perfectly good choice. Now we find the slope, y sub 2 minus y sub 1, x sub 2 minus x sub 1, okay? And then once we find our slope, we put it into this formula, where here's our slope, and then we use one of the points, and it looks like this is the point they used, y sub 1, and then x sub 1. Good, so distribute, combine like terms, add 5.7 to both sides, and then ultimately, this is the equation you get. Okay, so let's type that into our calculator, and we see what that equation looks like. So let me go over to y equals, come down here, and then negative 0.95x plus 7.6, enter. Okay, that's another line, and it looks like it's going to graph it in red. Let's graph. So there we go. So I have my equation. Here is the author. He chose these 2 points. That's the equation. Those are the values he chose. So let me see. That's trace. Let's hit trace. And it was the 2 point, yep, the 2, 5, 7. So that's that point right there. And the next one was the 6 point, there, the 6, 1.9. Okay, so they're both pretty good approximations. You know, at this point, we don't really have a way of judging who did a better job. They're both pretty good. But obviously, we're going to need some sort of mechanism to decide who did a better job. Right, so let me label these. Okay, so the red line was achieved by going through this point and that point. And this point right here was the ordered pair 2, 5.7. And the other point was that one right there, which is the ordered pair 6, 1.9. Okay, so the author found the equation of the line that goes through those 2 points, and that's what this is. Y equals to negative 0.95x plus 7.6. Okay, on the other hand, when I did this, I went through the point that went right through there. That was the ordered pair 0, 5.8. And this point right in there oops, this point right in there, which was the point 5, comma 2.8. And after all my work, I got the linear equation y equals to negative 0.60 x plus 5.8. Okay, two perfectly good guesses for a line that expresses the negative linear relationship that exists between these two variables. Okay, so graph both scattergrams in the line, and then use our results to predict what happens when x equals to 3. Okay, and that's where we really get to the heart of all this. We want to be able to figure out a linear approximation, a line that expresses that negative linear relationship, so that we can use that line to guess the result, the outputs of new inputs, right? We don't want to use this line to predict things we already know. Why would you do that? But if we have a new value, we can use this line to approximate new things. So, for example, going back to this guy, remember this was foot length and this is height. If I establish that this blue line does a pretty good job, you know, that one doesn't do a very good job, does it? How about if I can concede that this blue line does a very nice job of approximating things. When you give me an input, a new foot length, you know, some new person, their foot was measured, and it turns out that they were, you know, approximately, like say, well, okay, fine. Let's say exactly 32, this is in inches, I would guess. So, or their shoe size, 32. Anyway, there are 32 foot length. And then you go up here, and then this would be my very, very best guess for what the height of that individual is. I could be wrong. This isn't saying it's going to be exactly this every time, but it creates like a nice little place for me to guess, and the very best guess is there. If I had a region, it would be better to guess like a little region, right? So I would guess a little region around here. But if I had to pick one singular number, well, I would pick the value on the blue line as my best guess. It could be wrong. It's possible that he's actually really tall for that shoe size. Maybe he's way over here, super tall, given that he only has a 32. Or maybe it's weird. He's like super short, given that he has a big foot, right? But my guess, my very best guess, would be to go right in there, right? So that's what we want to do. We want to use our lines that approximate that relationship to do our guess. Okay, so when x equals to 3, that's going to be 1, 2, 3. Here is 3. 1, 2, here is 3. When x equals to 3, well, I can use my green line to guess an output, or I can use the red line to guess an output, right? Just because right now I have two guesses. And so that just comes down to plugging in a 3 into this equation or plugging in a 3 into this equation, right? X equals to 3 means we just plug it into there, or x equals to 3, that means we just plug it into there. Good, 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 good. Okay, so keep in mind that I only have 2 because I wanted to demonstrate that there's more than one correct answer. So this isn't about finding the unique, most correct answer at this point. There are different equations based on sort of your guess of which points would best make for a good linear approximation, right? A good line that describes the negative linear relationship of the points in our scattergram. Okay, so let's just stick to that one, just because that's the one that the author did. Okay, so if we stick to the one that the author did, the author used this point, and then they created this red line. And so if x equals to 3, it's going to be approximately this tall. The output goes approximately that much. Right, let me erase the other one then. So let's just stick to that. So we're going to go there, and then we're going to go across. And it's somewhere over there. This is my y output, right, based on x equals to 3. Good. Okay, so let's just plug in 3 into there. Come over here and say when x equals to 3, based on the author's guess, it means that the y equals to negative 0.95 times 3 plus 7.6. So let's calculate what that is. Negative 0.95 times 3 plus 7.6 gives me 4.75. Okay, so my best guess is that the output of this is going to be 4.75. That this is going to be about 4.75 in that guy. Right? When the input x equals 3, my best guess is that the output is about 4.75. Okay, and so this is what the author, your book, printed. Same thing. Okay, and we have that best guess based on that prediction of that line, which just included, the points that the author wanted to include. Okay, so now we're going to define something called a residual. A residual, right, the difference between the observed value, what you actually see in your table, in your data, and the predicted value, which is based on that line. So for example, when x equals to 3, the output that we observe in our table is actually 5.2. Let's go back to our original table. When x equals to 3, the output we observed was 5.2. Okay, so the difference between the predicted value, the value along my line, right, when I created this line and I used x to predict what would happen, I got this point right there. So they were off a little bit. There's like a little gap. Let's see if I can zoom in some more. Right, so the values on my blue line are what I'm using to guess things, right? That's my prediction. Prediction is a guess. And then the observed values are the actual data points that I saw, and that's what these little blue squares are. And so there's a little gap here. There's a little bit of space there. There's a difference there. That's what we call the residual. Residual. Okay, so that's this definition. The difference between the observed value and the predicted value. So observed minus predicted. Observed minus predicted. That's important because the sign matters. So in this case, the observed is actually bigger than the predicted, so that when we subtract them in this order, we end up with a residual that's equal to 0.45. If, on the other hand, we had a little blue square, a little observed value, let me just kind of draw one in here. Let's say that we had a little bit, like a little observed value there. It's not there in our table, but I'm just throwing it in there. Then the predicted value for 1 is way over here. Right? I would be predicting this much for 1, but let's say my observed value is this. Well, in a case like that, then this is my residual, and it's below, right? In this case, the predicted value is a number that is bigger than the observed value. Therefore, this number will be smaller, that number will be bigger. We'll end up with a negative, right? So this will be a residual, and it'll be negative. Negative residual. Okay, so sometimes the residual will be negative if the observed values are below our predicted line. Sometimes the residual will be positive if the observed values are above um, the, the predictive line. So um, we want to use that to judge how good our line is as a predictor to the relationship that exists between the explanatory and the response variables. Okay, so how do we decide which line does a better job? There's several ways to think about that. Remember, back to up here. Where to go? Back to this. There were two guesses, the green line and the red line. And I can use either one, and they both give me good predictive values. But which one does a better job? Right? Who's to judge which line is better? Well, one way to do that is to find the line that creates the smallest sum of square residuals. We're going to find the residual of every single value in our original data set. Remember, that's the distance between the point and the line. Find all those distances. Sometimes they're positive, sometimes they're negative. So you don't want to just add them at that point. Otherwise, you're just going to get something that's close to zero. Things will kind of cancel out. What we want to do is make them all squared. That way everything is positive, and then we add them down. Okay, so let's look at an example from over here using this. See what we're talking about. Okay, so let's say that I'm thinking this is a very good approximation to all of these dots, right, to this scattergram. What we're going to do is, first of all, find the residuals for every one of these values. The residual is these lines, the line that connects this point to a point on the blue line. So it'll be a little line right there. And this point to the blue line, and this point to the blue line, right? Sometimes they'll be negative. So if it's below the blue line, we have a negative residual. If it's above the blue line, we have a positive residual. So let's show the residuals. There they are. Right? We can visually see with this program the lengths of those residuals. This is a positive residual from there to there. From here to here is another positive residual. There's a little one in there, it's hard to see. Then this one and this one, this one and this one, right? And then there's a bunch below the line from here to here. This distance, which is going to be a negative value. This distance to this distance, which is going to be a negative value. Okay, so then we're going to square them all and add them together. Add up that number, and that'll be a number that kind of gives you an indication of how well this line here, this guess, how good of a job did it do to approximate the relationship in this, the positive linear relationship that exists here, right? So if I can come up with another line that does a better job, that reduces the sum of squared residuals, then I would consider that to be a better guess. So for example, let's move this along. Let's say it does that, and let's say it goes way down here. Maybe I'm guessing that this is a good line. Do you see that if I guess that this, let me turn off these things for a second. If I guess that this is a good line, right away we can judge that that's a terrible line, right? All the dots are way above it. It doesn't do a very good job. Or maybe even worse, let's say that. Somebody guesses that this is a good approximation. It does a sort of a good job of looking at the direction, but it seems to be systematically off, right? Okay, so if I calculated all the residuals, the line from there to there, the line from there to there, the line from there to there, we would get all these really long lines, right? And so if I squared all of these lines and added them all together, that's going to give me a higher value. Does it show sum of the residuals? Okay, I think that that's it. So this computer program here automatically gives you the sum of the squared residuals. So that's what this is, this sum right here. Okay, so then we move it and see how that sum is getting smaller. We're doing a better job. And then we come up here and, oh look, we're doing a better job. That's all the way down to 68. So what's the smallest I can get it? If I just go up, oh, 60, 50s. 51. Oh, now it started climbing back up again. Okay, so it looks like low 50s seems to be doing, the best job somewhere around there. And then maybe tweak this a little bit. I don't know, maybe there. Okay, so I can, whoa, I don't know what happened. So I can tweak this around and play around with it until I get the smallest value I can possibly get, right? I'm staring at this number down here, which is the sum of the squared residuals, right? The program, let's zoom out a little bit more. The program automatically adds them up and shows you what they are right here, right? So if I go way off the reservation here and guess it's something like that, that's terrible, right? That line right there does not do a good job of approximating the scattergram, right? It's even in the wrong direction. This has a negative slope. We're convinced this has a positive slope. And if I find all those residuals, the line from here to there, line from there to there, line from there to there, all those residuals, right? Those are long lines. Some of them are positive, some of them are negative. But then if I square them all and makes all of those values positive, I add them together, that's what I'm going to get right here. Okay, but as you can see, that's a pretty big number. I can do a much better job if I play around with this and move it around and come this way, come that way, until I get to something reasonable. Looks like maybe, see if I can get it back down into the low 50s. Okay, so that low 50s, down, 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 down. 51. Can I hit 50? Ooh. Nope. Okay, looks like just by playing around with it, looks like 51 flat is the smallest I can get it to be. I can't, yeah, so just playing around with it, that's the smallest value I can get. Let me get rid of those residuals. There we go. That's my very best guess by just kind of manipulating and playing around with it. Notice that this line might not actually go through any of the original values. That's okay. It still does a very nice job of showing the relationship, the positive linear relationship that exists between the explanatory variable and the response variable. Okay? All right, one more. Well, okay, let's go back to this guy. We'll come back. Okay, so those distances are called residuals. You got that. Those little distances are residuals. If you're below, you have negatives. If you're above, you have positives. So you can't just add the residuals. The sum of the residuals is going to be close to 0. What we want is to square them all. Okay, the least squares regression line is the line that minimizes the sum of the squared residuals. They're also called errors. This line minimizes the sum of the squared vertical distances between the observed values of y and those predicted by the line y hat. Right? So line y hat will be the line that is the least squares regression line. Okay? It's the best fit line according to this criteria. There are other criterias out there, but this is the most popular one and the only one we're going to study in this class. That's all we have to worry about. When I say you find the best fit line, this is what I mean. The least squares regression line. Okay, well, hopefully that means we have a pretty good idea of what it is, but how do we find it? Okay, well, unfortunately, this is where we go back to one of those mysterious formulas that I can't really explain. Because it's sort of it's way outside the scope of this class. But again, I'm going to have to ask you to trust me that there is very solid mathematical foundation. It's a very solid mathematical foundation for this, but it's just a little outside the scope of our class. So you are not responsible for knowing where this formula came from in this class, but you are responsible for knowing how to use it, when to use it, and how to calculate it, and how to apply it. Okay, so this is what the formula is. The little hat, remember, the little hat represents the least squares regression line, the best fit line, and it's equal to this. The notation is a little weird, but this is akin to, remember, our linear equation, y equals to mx plus b, right? This is where m equals the slope, and 0 comma b equals the y-intercept. Y-intercept. Well, we're doing the same kind of thing, except instead of using the letters b and m like we usually do in algebra, in statistics, they've decided to switch it over to b sub 1, where b sub 1 is the slope. This is b sub 1 equals the slope. And 0 comma b sub naught equals the y-intercept. Okay, and here is the formulas for them. I know that in algebra, when we're working with this formula, the m was equal to y sub 2 minus y sub 1 over x sub 2, all that stuff. Okay, well, not here. Here, the slope of the least regression line is equal to this. We need to find the sample standard deviation of the y-coordinates divided by the sample standard deviation of the x-coordinates, and then multiply it by r. Remember, r is the correlation coefficient value that we calculated in the previous section, or in this at the beginning of this video. Okay, so that'll help us find b sub 1, the slope. And then that number is being used to calculate the next one. So you have to find them in this order. You have to find b sub 1 first, the slope of our regression line. And then once you do that, then you can find the b sub naught coordinate value, which is going to be the y-intercept 0 comma b naught equals the y-intercept point. Okay, and that's going to be equal to y bar minus b1 x bar, right? And that'll give you your y-intercept point. Once we find these 2 points, we just plug them into there, and we'll have our least squares regression line. Okay, note that x bar is the sample mean, s sub x is the sample standard deviation of the explanatory variable x, y bar is the sample mean, and s sub y is the sample standard deviation of the response variable y. Okay, so let's go back to this up here. Where's our thing? Okay, we've been working with this table, right? We started with this table, then we created this ginormous table, crazy painful thing to figure out the value of r. Here's r. Once we have the value of r, we're going to need the mean and standard deviations for the x and the y coordinates, which we have right here. So within this and this guy, I have everything I need to find the equation of the least squares regression line, the best fit line. Okay, so let's see. I need b sub 1 first. B sub 1 is equal to r times, oh, you know what? Let me check something. Oh yeah, y over x. I always forget that, with terrible memory. So this is s sub y divided by s sub x. So b sub 1 equals to negative 0.95164 times s sub y, which is equal to 1.8239 divided by s sub x, which is 2.4121. 4121. Okay, so let me just type that in my calculator. That's 1.8239 239 divided by 2.4121 times negative 0.95164. That gets me a value of negative 0.71, let's round it to 96, rounding to 4 decimal places. And once I have that value, then I can calculate the b sub naught value. And the formula for that is b sub naught is equal to y bar minus b1 times x bar. Okay, so b naught is going to be equal to the mean of the y's, that was this value over here, that would be 3.9333 minus negative 0.7196 times the mean of the x's, which was right over here, 3.6667 was the mean of the x's. Okay, so let's type that into my calculator. Remember, a negative times a negative is a positive, so I'll end up with 0.7196 times 3.6667, and then we add that to 3.9333, and I end up with approximately 6.5719. Okay, so then I bring that together to our formula, and we get that y hat, the sum of the best fit line, is going to be equal to this as my slope, negative 0.7196x, and then this as my y-intercept, or 0 comma this is my y-intercept, 6.5719 approximately. Okay, so let me put that into my calculator. We had one approximation was the green one, that's using this point and that point. One approximation was this red line using this point and this point. But which one is better? Neither. The best one is this one. The best fit one is this one. At least one characteristic, one way of describing what the best one would be is the least squares sum residual. X plus 6.5719. Enter. Okay, and now let's graph all three. Oh, actually, let me change the color. Enter. And what do we want? Magenta, green, orange. Let's go with orange. Enter, enter, enter. Okay, so graph. There we go. The orange one turns out to be the very best fit line, right? The least squares regression line. Okay, so the green one was a perfectly good guess. The red one was a perfectly good guess. But one way to grade them, to see which one does a better job, is to find all the residuals, square all the residuals, add them together, and the line that produces the smallest sum of square residuals. That would be one way to judge that that's the best fit line. And the orange one is the one that's going to do that. Okay? In fact, I wonder if... Okay. So let's go to another example. Okay, so let's look at this example. Examples finding the least regression line. Okay, so this was from section 4.1. We've already worked with this example, 4.1, so we're not going to reinvent the wheel. We're going to recycle some of the information we got from before. Remember that this involved a question of how long it takes to drill an additional 5 feet, where the explanatory variable is how deep you are when you start drilling. So if you're already at a depth of 35 feet, how long in minutes does it take to drill an additional 5 feet? So 5.88 minutes at that point. And then if you're at 145 feet deep, it takes an additional 6.42 minutes to continue to drill an additional 5 feet, and so on and so forth. So using the work from 4.1, I'm just going to copy that down and put it in here. Okay, so this was from section 4.1. You can go watch that video if you don't remember it. Section 4.1. It's how we calculated the R value, very painful, using our calculator. But we have our R value. We also have the mean of the X coordinates, the sample standard deviation of the X coordinates. We have the mean of the Y coordinates and the sample standard deviation of the Y coordinates. So we have everything we need in this little box as well as the R value. So we can proceed to use our formula. So remember that B sub 1 is going to be equal to R times S sub Y over S sub X. So B sub 1 is going to be equal to 0.773 times S sub Y, which is 0.780774, divided by S sub X, which is 52.22874. So B sub 1 is going to be equal to 0.011, and then several fives. Let's go out to 5, 6, approximately. Actually, let's go one more. 5, 5, 6. Seems like a pretty good approximation. Okay, so that's a pretty good approximate. Okay, so now once we find B sub 1, we got to find B sub 0, B sub naught. Remember that the formula for that is Y bar minus B1, which we just found, times X bar. Right, so again, everything we need is right there. So B naught is equal to Y bar, which is 6.9858 approximately, minus the value we just found, so that would be 0.011556, times X bar, which is 126.25. Okay, so let's type that into my calculator, see what we get. So that'll be 0.011556 times 126.25, and I get 6.9858 minus that answer, and I'm getting approximately 5.5269 approximately. Okay, so now we get to bring that all together into my Y hat value, the best fit line, the least sum of squared residuals line. which is equal to the b sub 1 value, x, plus the b sub naught value. So y hat equals to approximately 0.011556 x plus 5.5269. Okay, so what does that mean? That means that if we create our scattergram, this is the line that does the best job of approximating it, of approximating the relationship, the positive linear relationship that exists between these two variables. All right, let's confirm that. Let's go back to our calculator. Go to Stat, Edit. Okay, and then on list 1, I've inputted all the coordinates of my depths. And then on list 2, I've listed all the coordinates of my times. Okay, so list 1 and list 2. I'm going to go over to y equals. Let me go to y equals. I need to clear this for a second. Okay, so we're going to deactivate, make sure all the other equations are deactivated. So I was just using these other equations, and they might have this. They might have looked like this. Okay, so if I tried to graph my scattergram now, it will try and graph these lines as well, and I don't want that. I could either erase them, but I might use them in the future, right? So let's go to the equal sign, hit enter, and then when you move away, you see it's no longer dark. Hit enter, move away, it's no longer dark, right? Looks like that. Plot 2 and plot 3 are deactive, so that's good. All of these lines are deactivated. The only thing that's active right now is plot 1. So let's go to plot 1. Hit enter there. It's on. It's a scattergram. List 1 and list 2. Everything is exactly the way I want it. So let's hit zoom number 9, and there's our scattergram, right? This is the explanatory variable, which is the depths at which we start drilling. And then here's the response variable in the vertical axis, which is the time it takes to drill an additional 5 feet deeper, right? Okay, so we can see that there's a positive linear relationship. We've confirmed that the R value is 0.773, and then we used our table for critical values to establish that there is enough sufficient statistical evidence to conclude that there's a positive linear relationship between these two variables. Good. Okay, so all of that was what we did yesterday. But beyond establishing that there is a positive linear relationship, now we want to find a line that does a good job of approximating that. Okay, and the sum of least square regression line is the one that we're going to choose. Okay, so now let's come over here and we're going to type that in there. Y equals, let's come down here. That's going to be 0.0, the extra 0.0115556 x plus 5.5269. Enter. Okay, so now I can graph that, and there it is, right? It does do a pretty good job. I can confirm that that magenta looking line is doing a pretty good job of approximating my ordered pairs here, right? Some of them are above it, some of them are below it, so it's sort of a way of describing the average of all of them. And it's capturing the direction and the general sort of slope. So it's doing a very nice job of communicating the relationship, the positive linear relationship that exists between these two variables. Okay, so that line is the best fit line by using the sum of least squares regression as the criteria. Okay, so what do we want to do with that line once we establish it? Well, we want to use it to make predictions about values we don't know yet. So if a new value is recorded, say here, what's my best guess for how long it's going to take to drill an additional 5 feet? Well, my best guess is going to be the value of that line, right? That line is going to be my very best guess for any new ordered pairs that we input. Good. So, okay, so we agreed around estimates of slope. Okay, so here is what the author came up with. Okay, that's what we got. And if we wanted to predict what happens at 130 feet, then we would input x equals to 130 feet. So when x equals to 130, my best prediction, right? Prediction is a fancy word for a guess. My best guess is going to be the y value equal to exactly this, the 0.0116 times 130 plus the 5.5273, which means the y hat value is 7.035. So on our calculator, let's just do it on here. Just to visually describe what that means. At 130, wherever that is, I'm not really sure where it is on this scale. I just want to visually point it out. So when x equals to 130, you know what? Actually, I could do even better, right? Because I can. Is there a value that's 130 in our table? Yep. Okay, here it is. It was 130. This is the observed values. 130 and 6.93. So let me go back to my calculator. Let's go to trace, and then 130 is that one. Oh, great. It was really close to the magenta, so it's going to make it kind of hard to visualize it, but okay. Apparently, it's this one. So apparently, this is an input value of 130. And even though there's not much space there, there is the blue box and then there's the magenta value, and they're not exactly one on top of the other. There will be a little gap there, right? Which is kind of hard to see here. They're very, very close. But the value on the magenta line is the result of my least square regression line, which is the 7.035. On the other hand, the 6.93 is the actual observed value. Okay, your author did a better job than this. So this is approximately the same as this graph, right? So this is what your calculator looks like, but it just looks a little better over here because this graph does a better job of creating a little bit of space between the two. So here is 130. 130 extends right there. And so you see that this line is the line, the y hat line. And so if we evaluate that y hat line, we get that value there. And then this is the 6.93. So there's a little space that exists right there, right? That's the residual. Residual value. And this one is 7.035. 7.035, comma 130. That's my predicted value, right? According to my best fit line, it should take 7.035 minutes to dig an additional 5 minutes when you start at a depth of 130. However, the observed value, that's this guy right here, that observed value was actually that 130 matched with 6.93 minutes, right? So it was a little bit lower than this. So I said a minute ago that this line, the sum of least square residuals line, the best fit line, I said that that's sort of like an average, right? About half the points are above the line, about half the points are below the line. So we can think of that as the average. So we would say that the observed value is below average, right? The average is what we would expect, which is the 7.035. Okay. And that matches with what we hear. So the observed drilling time is 6.93. The predicted drilling time is 7.035 seconds. So the drilling time of 6.93 seconds is below average, and the residual is the space between the two, right? So the residual would come from subtracting those two. Okay. Well, this was fun, but is there a faster, better way to do this? There is. We could just have our calculator do the whole thing. So we found this equation, not this one, over here. We found this equation, very, very painful manner, right? If you had to do this whole thing by hand, you basically have to do everything that's on this screen right now, right? Given the original set of data, we got to put this on the list 1, list 2. We got to find the mean and standard deviation of this list, the mean and standard deviation of this list. Then we got to go through this whole process to find the R value, R. Then once you find the R value, then you got to go through this process to find the mean, to find the slope of the best fit line. And then you got to go through this little thing to find the y-intercept of the best fit line. So that's a lot of work, right? Or we can just have our calculator do it. So we can go over to y equals, and then let's go to stat, edit. Okay, so first of all, we got to confirm that we have all our x coordinates onto list 1, our y coordinates onto list 2. Okay, list 1, list 2. All right, so now you're only going to have to do this one time, and that's just to make sure that your calculator is set to the proper settings. So let's go to second, and you got to go over here where it says catalog. See, second, catalog. And then you got to scroll down, down, and you're looking for diagnostics on. Diagnostics on. There. Diagnostics on. Hit enter, and then it says done, and that's all you need. And it should save it from now on, unless you go back to default factory settings, or if you remove the batteries or something, then you might have to do this again. But it should remember it even if you just turn off your calculator and turn it back on again. Okay, so you only have to do this once, and now this is what you're going to do. You're going to go back to stat, and this time you're going to go over to calculate, and you're going to go down to where it says linreg ax plus b. It's linear regression line ax plus b. Okay, linreg ax plus b. Hit enter. And now tell it where the x coordinates are. They were on list 1. And the y coordinates, they were on list 2. Leave the frequency blank, right? Don't put anything in there. Leave the store blank as well. We'll deal with this one later. I just don't want to pile on right now. We're learning something new. So leave it blank, and then come down and hit calculate, or hit calculate, enter, and boom, there it is. Okay, so we get a linear regression, in the form of y equals to ax plus b. This is where the a is the slope and b is the y-intercept, right? So your calculator, the creators of the software in your calculator went back to using a different letter for the slope and the y-intercept just to add a little extra confusion. But the a is the slope here, and there it is. It's this one. And that's the exact same value we got from this whole crazy equation right here, 0.01155. And also the y-intercept, right? This guy right here, that's this, 5.5272. Okay, there was a little bit of rounding that happened, and that's why it's slightly different. And then this guy, the r value, 0.7728, right? We got 0.773, 0.7728. So this rounds to 0.773. So it's an even more precise answer, and it was just a few buttons away, right? Okay, so in this chapter, you're going to have to do it the long way. You can't use this shortcut to find the answers. They're going to be off by a little bit. And in terms of the exam, if I give you something like this, I would expect to see this table to show me how you got your answer. When we leave this chapter, you're no longer going to have to be required to do all of this. You can just go over to your calculator and do it the easy way, right? Lin reg. At least though, in this chapter, you at least can use your calculator to verify your answer, because I know it's very easy to go through this whole crazy thing and be off by just a little bit, and then that results in a very different answer. But this way, you can confirm it. And so if you get the wrong answer, then you know something is off, and it'll trigger you to figure it out. So first, double check. The first thing I would inspect is to make sure that you've inputted these values into list 1 and list 2 accurately. That's often a mistake, just a tiny little number off. You'll see that the R value is way off. Okay. And then if that is, doesn't fix it, if they don't match, well, then now you know that something is off over here, so you can go try and find it. Okay, but so we get both our linear regression and our R value this way. Let's go back to the online description of these things. No, let's go there. Okay, let's come back to this example that we had with Rossmann Chance. So we had foot length, we had height, here's foot length, here's height, and we create this scattergram. We could see that there is some sort of a positive linear relation that happens here, and we can guesstimate what's a good a line, just kind of eyeball it and kind of figure out what's a good line. So someone just kind of might think that this is a good guess of approximately where that line would be. Remember that in order to kind of grade them and qualify them, which one's better, which one's worse, one way to do that is to grade this guess by finding the residuals. There they are. Sometimes they're positive, sometimes they're negative. If I square all of them, then I get this. Now, this is a nice visual of what happens when you square all those values. You get this, right? So if I took this length right here and squared it, I would get an area. I would get the area of this square. Good? And if I took this little distance right there and squared it, I would get that little tiny little area of a square, right? So the benefit is that before you square them, some of them are positive, some of them are negative. But if you square them all, they're all positives, right? So now what we're doing is we're adding up areas. The area of all of these squares, the sum of these squares, squared residuals, is the value that we're going to use to judge the quality of that estimation. This one versus, let me move it around. How about this one? Right now, this line here, this could be a pretty good guess, and then it results in all of these little squares. I add up the area of all those squares, and then the sum of those areas would be how I qualify it. Currently, they add up to 60.86, right? Or maybe I move it around over here. Now they add up to 60.15, so it looks like that did a better job. Or maybe I move it over here. No, I messed up. I made it bigger. Now the area of all those squares adds up to 89.64. Okay, so the one that's going to do the very best job is the one that's the regression line. So if I just have the calculator compute it for me, that's this red one. The red one, let me erase all that, is the best fit line. It's the line that minimizes the sum of the squared residuals. Here are the residuals. Here are the squared residuals. Good. So that one does the very, very best job. Okay, so it's just a way to kind of visualize it. And back to this. So one last thing, interpreting the slope. So the slope of the regression line is 0.0116. Remember that slope is rise over run, just in general. So slope is rise over run. So whenever you're given some sort of slope, like let's say this slope equals to 0.0116, we can always convert it into a fraction by putting a little 1 there. And then let's think about our units, right? Going in this direction, we had depth in feet, right? How deep are you when you start drilling? And then in this direction, we had time in minutes to drill 5 feet. To drill 5 more feet. Right? How long does it take to drill 5 more feet? Okay, so there was some sort of a linear regression line, that best fit line that did something like that. So if we take any 2 points on here, so we take one random point right there, and then we go this way. Well, I should have put this line in blue. And now we're going to think about the little triangle that kind of goes this way. Okay, so it might not be up to scale, but if we think of this as 1 unit this way, that's the run, and then we go up by this many units, 0.0116, like this, rise over run. That means that for every 1 unit this way, which is feet, right, for 1 foot going this way, it takes 0.011 minutes, additional minutes. For each additional foot in depth we start drilling, the time to drill 5 feet increases by 0.0115 minutes. So for each additional foot that we go this way, 1 foot that way, each extra feet that we add to the depth, for each additional foot in depth at which we start to drill, the time it takes to do 5 feet of drilling is going to increase by approximately this many minutes, 0.0116 minutes. Good. When we get to these numbers, it might make it a little easier to figure it out in terms of seconds. 0.0116 times 60 seconds. What is that? 0.0116 times 60. That's about 0.696 seconds. Still pretty small. 0.696 seconds. That's another way of saying it. For each additional foot at which deeper at which we start to drill, it will take an additional 0.696 seconds to drill 5 feet. For each additional foot in depth we start drilling, the time to drill 5 feet increases by 0.0116 minutes on average. Interpreting the y-intercept point. The y-intercept of the regression line was 5.5273. To interpret the y-intercept, we must first ask a couple of questions. Is 0 a reasonable value for the explanatory variable, right? And in this case, it is, right? X was how deep you are before you start drilling. You know, how long does it take you to drill an additional 5 feet starting at an X level of depth? So 0 would just be the surface, right? So it would make sense in this case that it is a valid coordinate point. It's how long does it take you to drill 5 feet starting at the surface level. In this case, a negative X coordinate would make no sense, right? That would mean you're above ground, you're in midair or something. So it wouldn't make any sense in this case. So a value of 0 is reasonable for drilling data. This indicates that the drilling begins at the surface. The smallest observation in the data set is 35 feet, which is reasonably close to 0. So interpretation of the y-intercept is reasonable, right? And so we can interpret that to mean that at the surface, it takes about 5.572 minutes to drill 5 feet on average. Okay, one caution though, if the least squares regression line is used to make predictions based on values of the explanatory variable that are much larger or much smaller than the observed values, we say that the researcher is working outside the scope of the model, and we never use a least squares regression line to make predictions outside the scope of the model, because we can't be sure that the linear relationship continues to exist. What does that mean? So let's go back over here, for instance, right? So we have, let me erase some of these things. We had a scattergram of our data, right? And the smallest value that we have actual real data for is 35. And the largest one that we actually have real data for is when x equals to 190. So we like to say that we would use this model, 190, to make new predictions about values that lie inside here, right? This zone that lies between known data points, this is the scope of my model. It makes reasonable sense that this line here does a pretty good job of approximating what happens in that zone. We don't really know what happens beyond that. Is it true that this linear relationship continues? Maybe. Maybe it turns out that at some point it just kind of plateaus and then maybe it flattens out, right? We don't know that. And same thing over here. Does this linear relationship continue to go this way? Straight line? Maybe it does, maybe it doesn't, but we don't have any evidence of that. And maybe it does that. I don't know. Maybe it starts off being really hard in the beginning, but that makes sense. Is it possible that, yeah, maybe there's like big boulders that are very close to the surface of the earth, or maybe just concrete or things like that. So maybe it's really hard to drill at the very beginning. Maybe this spikes up like this, and then it gets really easy for a while, or much easier, and then it begins to slowly increase, right? Maybe that's the way it behaves, but maybe not. Maybe it is a perfect straight line. We don't know. That's why we like to stay within the scope of it. If you start using this line to make predictions about input values that are over here below the smallest value or over here above the biggest value, then that's when you're saying that's when you're working outside the scope of our model, right? You're making guesses that are like extra big guesses. They are no longer even connected to the or the input values that you're using are not within the range of the known data values. So there's even less confidence that this is a good way to approximate it. Good. Okay, I think that's a good place to stop. You should have everything and all you ever need to know about the material from chapter section 4.1 and section 4.2. Remember that we're not covering the other sections in this chapter. For us, we're going to jump ahead and move over to chapter 6 since we've already done chapter 5.